Hello everyone, so I'm Thanigai. So our group takes care of providing all security infrastructure, cryptography and network security components to the database and supporting products. So our team recently adopted OpenSSL into our ecosystem, and I'm here to talk about the experiences we had and what may be some suggestions for people looking for it. So as for what we're going to talk about, so mostly what kind of challenges we have when we have like a large scale software supporting enterprise customers, and what kind of challenges we face when looking into OpenSSL and the process of adopting OpenSSL, and what we might recommend for people looking to do versus also in improving OpenSSL itself for future adoption by other enterprise customers. Okay. So as you know, we are a leading software company supporting a vast majority of enterprise customers. Also, so our primary product is database, and we are also a large cloud infrastructure vendor. So these environments pose quite a lot of security requirements, and especially cryptography and network level security. Our portfolio includes operating systems, a variety of databases and applications like healthcare, HR, ERP, and so on. And we also have cloud. And the environments are not limited to a single levels. We have like a tiny to a extremely large scale environments. So our security solutions we provide need to meet all these levels of deployments and use cases. Okay. So what do we look for when a security solution is adopted under our products? Obviously, there is a whole lot of them. So first and foremost, it needs to support strong cryptography as the state of the art moves forward. So the industry does demand us to support those kind of technologies, algorithms, and so on. So whatever toolkit we use, that should be agile enough to bring in those technologies so that we can plan to expose to our customers. Performance is obviously key because of the range of scale in deployments. It needs to be able to perform in all kinds of environment. It could be like we have like hundreds of connections hitting the servers per minute. It needs to be able to serve those kind of requirements, and while also be able to decrypt data that can scale from a few gigabytes to terabytes. So it needs to be able to perform to these kind of requirements. And obviously the toolkit must be modular enough that adding new features or algorithms should not be an issue should a need come. So that kind of architecture does help. And obviously you need to be able to patchable. Right? And FIPS is an extremely important requirement for us. So we do have a large scale of government customers and banking customers who do have their own requirement to deploy FIPS certified solutions. So it does translate to us meeting those kind of requirements. So FIPS is paramount. And platforms wise, yeah, Oracle supports a broad range of platforms. Like to name a few, we have Linux obviously, and AIX, Windows, HPUX, Solaris, and so on. And depending on how the technology move forward, we'll adopt new platforms, shed old platforms, and so on. So it does need to be agile there. Compatibility wise, yeah, we do have customers who would deploy some database today, but maybe hesitant to move to a new different version unless absolutely necessary. So, but the ecosystem does demand that we need to remain compatible with the older versions as the newer clients come into the picture, or new servers talking to older clients. So all these things, the mix is extremely important. So the backward compatibility is a major requirement for us. So lastly, long-term support. So it's stemming from the previous point. When we have customers running some versions for a long time, the security solution plugged underneath that needs to be patchable. So we need to be able to receive, apply security fixes and other bug fixes and be able to support it for the long term. So it does require the library to be able to provide that kind of long-term support going. So just to give an example of where the range of products that do require encryption solutions. So it's a vast, right? So you have network. That's where the clients hit the product, and then you had to authenticate the user, and then when you need to get the data from the disk, you decrypt it, and there are other solutions that need to work in conjunction with all these things. You have the key that needs to be securely stored. Backup obviously is very important, and that needs to be encrypted as well. So that does employ the technology. And lastly, you have to export data to another database. So again, encrypted solution is used. Right? So this is just an example. So we do have a few other scenarios where security is paramount. So I just thought I'll show a sample here. And as noted, all of these need to use FIPS certified solution. It's not an option. All right. So we talked about now what a typical security solution would need to meet. Now, why OpenSSL, right? So we did use. Okay, we are a recent new entrant to the OpenSSL area, so we were using some other commercially supported solutions before. This is a recent adoption. So why, right? Obviously, it is of the other security libraries we evaluated, this one is the one that came most close to the feature matrix we had, right? It was able to support almost a large amount of features we do support, and that's clearly when you're there. And the performance-wise, it has been proven because it's already in use in a few of the server-level products, and performance is not a question. And at the time we were looking at it, 3.0 was just a concept, right? So it was shortly after the Heartbleed thing occurred. 3.0 was not even a concept at the time. If I'm not mistaken, it was 0.09 something, and 1 was just barely making the waves. So 1 was what we are looking at the time, but it uses the engine-based infrastructure to support other crypto modules underneath, which was not exactly what we were looking for. So it needed the provider-based model, so which was only coming in 3.0. So we did make plans around adopting 3.0 because we did have some plans for adding newer algorithms and other kind of infrastructure using the provider model. So 3.0 was the chosen candidate. And the performance-wise, it does have the promise of enhancing as per the hardware running underneath. So to give an example, the Intel instructions, they were utilized by the OpenSSL library. That was a big plus for us. And the last point is, as I mentioned, I think shortly after Heartbleed, there is a industry-wide participation, renewed interest in order to support this library, because I think it was realized that this library is in use in a vast set of products, which means the security would be at risk if it is not maintained as per the usage. So the renewed interest definitely is a plus for us, because it does show that there is clearly a motivation to keep it organized and secure and maintained for the long term. So that so all of these points allowed us to nail on OpenSSL, and we did venture down in adopting this in our product. Right? So how did we go about it? So like I mentioned, 3.0 was still not available at that point. So we did start with one, and so I think the understanding was that the APIs will largely remain compatible with minor changes expected in 3.0, obviously, and the provider-based architecture. Right? We took care of all the basic stuff with the 1.1, and when the 3.0 the developer release was announced, we moved to 3.0 and made sure that everything continues to work, and incorporated the FIPS provider, because that's it's not technically needs a new development from our side, so we did add FIPS, and that way it is on par with all the features that we were supporting before. Right? I say all, but it's not exactly all, because the gaps are what came next, and those two features, the integration with the hardware security models and smart card, and support for the Microsoft's crypto next generation. So these two were existing features, but which were not available in OpenSSL at the time. I think 1.1 had some engine modules written for this purpose, but 3.0 did not have that, and I believe at the time the direction was to for the HSM support use OpenSC, and for the CNG there was no existing solution. So that was what we were facing, and as our own release timelines were cutting in, we could not wait for somebody else to do it. So instead, what we ventured on was to write our own providers to support these features. So I'll go over those details for subsequent slides. And so that was the immediate thing that we did, and that brought us at par with all the features we are supporting with the existing, the previous security solutions. And then came the enhancements, the 1.3, adopting 1.3 and Cypher suites and all that, and two more features which were new features that we are considering for database. So I'll talk about those in the subsequent slides. And once these were done, we were ready to release. So that's our short version of what we went through. Okay. So the gaps I talked about, which needed us to write our own providers. So the main requirement for that is to support private keys living on black box type of containers. So two of them are basically the hardware security modules, the smart cards, which won't give out the private key, and also the Microsoft key store, which again holds the client's identity, but you're not expected to take the private key from that, right? So all these things needed support. Work in a TLS environment where we need to sign the data using the private keys living on these things, and the extent for crypto next generation, which was a new requirement. So for these, how we did was to add provider to route the signing calls over to the new provider and get the blob signed, and then continue the TLS operation. But it did require the provider because there is no other way we can plug in the private key into the OpenSSL TLS code. Right? And the next one was exporting the crypto context. So this is about enhancing the performance of our applications, which needs to be able to hand off connections to a different process, which again has to start bootstrapping all the way from the TLS and then renegotiate with the existing client connection. So instead, the solution we thought about was to export the local security context over to the remote process and provide a seamless and transparent way for the client to continue talking to the new process, so that the handshake overhead is not incurred in the new process. So it does improve performance tremendously. And so that needed us to modify the code so that we can support this kind of thing. The last one is injecting a application secret into TLS key, so that we can strengthen the existing TLS session with a secret that is shared by client and server. This is not sent over the network. This is this is shared by out-of-band means, so that it does increase the strength of the key. So as I talked about for PKCS 11, the TLS signing with the private key living in this HSM smart card, that was the primary motivation, and there was no built-in provider available in OpenSSL at the time. I think even now it is not commonly available. There are some vendors still writing it, but it's not readily available, not bundled with the OpenSSL. Right? But we didn't need the entire PKCS 11 specification implemented. We just needed the TLS signing operation, because this is to support the private key living on the device. So we did our own provider. And the same thing is extended to support smart card as well, so through the PKCS 11 interface. Okay. And for the certificate store, although the requirement was primarily from a Windows environment, for that we added a provider called External Key Store, which will talk to the Microsoft Cert Store specific driver that we wrote. And that again will talk to the actual Microsoft APIs to get the signing done. Now the way this is done is that is generic enough that you could, in theory, use it for some other operating systems which have similar mechanisms. For example, you have a laptop holding private keys that could be used to identify a client, could be extended to talk to those operating system provided APIs to get the signing done, so that the TLS can be seamlessly continued. So we are looking at adding macOS keychains. That is the potential improvement there. And this is about exporting the context. So it said transparent and seamless export of context over to a remote process. So the motivation is that the driving feature is that we have a server pool which consists of pre-spawned servers which are waiting for a client connection to come in. And we have several clients connecting to the server pool, but not all of them are utilizing the server all the time. So they can go idle in and out. But the server doesn't have to be tied to a particular client. So you have a broker that is multiplexing the connections with the server. So that way a server's utilization is greatly improved. So it does improve the overall performance. But then the problem was, all of this works in a non-secured connection. So when you have TLS in the mix, which was a requirement, so when you put TLS in the mix, it does require that each server, when it is handed off a connection from a client, it needs to establish TLS and to do the handshake and again set up the keys and all that. So it adds to the overall cost of transferring so which is extremely time consuming and obviously impact the performance. So how we attacked this problem was to export the TLS context from the server and hand it off to the next server that will pick up the connection, so that the new server that picks the context doesn't have to repeat the TLS with the client. So it can simply import the context into its TLS security context and continue the data exchange as usual. Now the client doesn't really become aware of this happening. So as far as the client is concerned, it is just talking to one server, and so it eliminates the overhead of establishing new TLS each time this is handed off. So it does extend our feature that we have with non-secure connections to the same level also to TLS. So in our own measurements, it did improve performance by about 25% just by doing the context export. So that was a great news for us. And for this feature, sorry. So we did have a requirement to enhance the TLS keys for various reasons. So one reason is this was a time when the quantum crypto was not yet available; it was still in development. So that was one motivation. How do we enhance the strength of the key? So the accepted workaround is to add an application-defined secret into the TLS keys to improve its security, and that can provide quantum resistance. So how we did was to the client and server, as part of an out-of-band process, they would establish a shared secret, which does not imply anything sent over the wire. So this is not something an attacker will be able to come into the knowledge of. And the server is then added to the TLS session keys, but it did require us to modify the code to accept the secret from the applications on both sides. You have a client sending the secret down to its own TLS stack, and the server doing the same thing on its side. There is just a signal level coordination needed between these two, that hey, I did this, and why don't you go ahead and do it, right? And for 1.2, it is automatically done. For 1.3, we made use of the key update TLS message. That's a new in 1.3. So the client, after adding the secret, it will send the key update message over to the server, and server will do the same thing and send the confirmation back. So then they are operating with the updated key. So this way, even if an attacker were to somehow get the key that was derived as part of the key exchange process, this key would be different because you're using a secret that is not sent over the wire. And so that did improve the security. So what kind of challenges we ran into? Obviously, at that time when we started, the documentation was much less than needed. I think it did go through a good amount of revamping, but we started with something that's not so user-friendly. So that required us to read the code pretty much. Every time we get stuck, we had to read the code to understand it. And that in itself is now no walk in the park. We did struggle in that process too, especially also because we are new to OpenSSL. That did pose a lot of challenges. We did hit some performance snags because with the 3.0, the providers added the mapping tables and then the error strings, which is like a huge swath of data that needs to be done, and every time a server comes up, it needs to go through all this, and that added to the startup cost. At some point, we decided to use a pool of servers. The one we saw in the earlier slide. That's part of the reason is also to reduce the latency, startup latency. Yeah. And for 8 years, we had an issue for some time because we had an in-house solution that used Intel's IPP library, and this solution was compared with the OpenSSL based solution, and it was not in our favor. So that sent us to spin on efforts to improvise on the performance. But I think IPP has a provider integrated in 3.5, which is great. So it actually has improved for the much better in 3.5. And I think there are still more ways to go, but right now it looks far better. Right? With the threads, we had issues with the locking. That's just unusually excessive. I think again with the 3.5, it does feel much better. But it was again a problem for us, which cost us to spend. With memory, we ran into problems in timing, when to clean up. It's not necessarily only due to the OpenSSL itself, but in our own product architecture, it's quite complicated, and to find the perfect point in time to get it free memory, it was a challenge. Eventually, we got around to it, but it definitely burnt cycles. Again, so from point one, we had to read source code if something doesn't work or it got stuck, but then source code is not easy. So eventually got around to using it, but yeah, it's to give an example, there will be macros writing like a pages and pages of functions, which not easy to debug. It's all right. Is that all right? So yeah, we are now using a popular toolkit which gives us all these great features, but then is it really good? There is a price to pay for that. It means that there is security bugs found all the time, or at least potentially found all the time, which will keep us on our edge because our customers get nervous every time they hear about security issues. Now, just to give a comparison, before adopting OpenSSL, when you're using commercial toolkits, obviously it is up to the vendor who's supporting it, and they can usually work out embargo with the person who found the bug, and they can negotiate and find a balance so that when the vulnerability will go public, so the products consuming have time to react. With OpenSSL, there is no such guarantee. So we need to be at the ready to implement fixes or even implement mitigations at the flick of a switch. So that definitely was a concern. So we have to design and devise a specialized pipeline just to take care of this, so that any fixes or workarounds that need to be employed, we are able to immediately push it through the build system and integrate in the huge set of products that need to be supported. It could be brand new release or something that released like 5 years ago. So all of them need to be able to receive the security fixes quickly, so that was not previously the case, but with OpenSSL we did have to do that. So that's a concern and a challenge, but we were able to manage that. So what would we recommend based on our own experience? Right? Threat safety, under, like I said, our systems are expected to perform under extreme load, and the threat safety and the performance is very critical. So that can be tested for and maintained, and the provider architecture could use some improvements. So while we are writing our own providers, we did have to again debug the provider abstraction to understand how the provider is supposed to work. So it was not, the documentation was not able to cover everything, so that was a challenge we faced. And so that can be more streamlined. And so documentation in general to cover complex use cases. I think the man page based approach works when you know what you're looking for, but there are situations where you may need to cover which is not covered by an API per se. So in those cases, the documentation, improvised documentation will be helpful. And for enterprise, testing is paramount. So increasing the amount of testing and improving to cover enterprise level use cases. So that will be very useful to enterprise level use cases, right? And lastly, how do you do diagnosing? So at least so our customers, we have integrated tracing and the diagnosability facilities, which are geared towards support teams able to read through the diagnosed output and be able to identify problems as quickly as they can. But I think OpenSSL largely still fits in the developer level diagnosing area. So it may need a visibility into the code to understand what exactly is going on. So that can be improved. So that's pretty much it for all I have to say.
All right. Hey, thank you for that presentation. So Thanigai has 20 years of experience in this realm, right? Yeah. And so you can ask him the hard questions, or the
not too well.
We do have a few minutes for questions, so we'll open that time up and let you take those, and then we'll maybe for the next 5 or 7 minutes, and then we'll go from there.
Yeah. Thank you. Yep.
Hi. I'd just like to ask about the, you talked about the TLS session handoff between, you had your, I can't remember what you called it, the broker and the various server processes. Yeah. I'm just wondering how that works, because I don't think OpenSSL supports that. So how did you make that work? Did you have to change OpenSSL to do that?
Yeah, so we have to do the changes in the source code. So yeah, it does require us to bring the key from the TLS context upwards to the application. Like I said, so it's a great improvement performance. And to be fair to the client processes, they're already connected, they're already authenticated with the server, and all of the server processes are on one system that is secure, right? So there is no need for them to repeat the handshake each time it is handed off. So this we saw as an extremely important, useful update to OpenSSL. So we did do that. So we had to plumb the entire way through. So add an API. But right now it's only we are using it. But I think our developer did initiate the conversation with the OpenSSL to commit eventually. Yeah.
Thank you.
Hi. Thanks for sharing all of that. As an enterprise, we can relate to everything. That's a very good thing about, because we face all this problem every day. I was more intrigued about the connection that you were thinking about. Normally, if you have a load balancer who knows about the back-end process, it's a sticky connection. So I assume for you, maybe the connection is rotating between the back-end processes. Like, how does that happen? Like, go ahead.
So is that respect to this one? Or?
Yes, exactly. Okay. So you have a broker process, and behind there are so many other processes. I assume it's kind of one box where.
These server processes are, okay, so if I take a step into the database architecture, so we do have multi-server architecture. So we have a database server process talking to the client directly. So that is one choice, and then we have multiplexing options too. So in this case, you have a set of server processes, but these are all database processes, right? So this is running as a process, but then you have data files sitting in the system. So now a client making a connection at any given point in time, one client exclusively uses that server, right? Now the optimization exercise was to have employ a pool, but then these are managed by the broker, so not necessarily rotating, but it detects the idling time in the client activity, and at that point the broker kicks the connection off to idling state, at which time the server is essentially free, right? It's just waiting for something to do. So instead of tying the connection with that client, it basically becomes free and ready to take up somebody else's work.
Okay. So, and I assume you don't use any extra hardware to offload any kind of signing operation and everything else. It's mostly on the host CPU.
Yeah, this is only sitting on the host CPU.
Okay.
Yeah.
And for the FIPS, do you use a certificate from the OpenSSL, because OpenSSL don't do that? So you use some third party like SafeLogic to have that FIPS validation?
So Oracle does its own validation.
Okay.
So we take care of that, because we also have the our own operating system that's the Linux flavor, which makes use of this certification.
Okay.
So
okay.
we do our own. Yeah.
Okay. So then the last question, did you recently kind of evaluated the recent offering that you're getting? Like you have AWS LC and you have Boring SSL, and we did all of that kind of performance benchmarking and all of that, like you know that nowadays the CPU, like all of that, they have AVX instructions, AVX 512, all of that.
Right.
So did you evaluated any of the recent offering and figured out which one is better in terms of, especially in the performance?
Nothing in recent. So this was a multi-year project. So we did venture on to this effort more than 5 years ago. So at that time, OpenSSL was the best fit, and we did make plans to, like obviously FIPS was a gap, and performance. When the snag was hit, we worked with the Intel team and get that IPP code integrated into OpenSSL. So that's what it's based on.
Okay. Yeah. Thank you. Thank you for sharing everything.